Welcome to The Explainer. Today, we're going to tackle a true classic in physics, a problem that, trust me, shows up on exams all the time: calculating the electric field of a dipole. If you can nail this, you're looking at some serious marks.
So how do you actually do it? How do you master this derivation and make sure you don't leave a single point on the table? Well, that's exactly what we're here to do. We're going to break it down step by step so you can solve it perfectly every single time. Let's dive in. Okay, first things first. Before we can derive anything, we have to build a solid foundation. I mean, you can't calculate the field if you don't really get what a dipole is, right? This part's quick, but it's absolutely crucial. So what is an electric dipole? It's actually super simple. It's just a pair of charges. One is positive, one is negative, but they have the exact same strength, or magnitude, which we call Q. And they're separated by a teeny tiny distance, which we label 2a. That's it. It's a fundamental setup you see all over the place, from molecules in chemistry to how antennas work.
Now, to really work with a dipole, we need this thing called the dipole moment, which we represent with the letter P. You can think of it as a little arrow that tells us how strong the dipole is and which way it's pointing. The magnitude is easy. It's just the charge Q times the distance 2a. But here's the most important part, the detail everyone forgets but you won't: its direction. It always points from the negative charge towards the positive charge. Remember that. It's going to be a huge deal in just a minute. All right, foundation set. Let's get to the main event. Our first major derivation, finding the electric field at a point that's right on the dipole's axis.
So, I want you to picture our dipole just sitting there. The axis is the imaginary line that runs straight through both charges. Now, we're interested in some point, let's call it P, that's also on this line, a distance r from the very center of the dipole. Our mission? To figure out the net electric field at that exact spot.
The logic here is pretty straightforward. Our point P feels a push from the positive charge and a pull from the negative one. So first, we calculate the field from each of those charges separately. Since those fields point in opposite directions along the line, we just subtract the smaller one from the bigger one to get the total field. Then comes the algebra, finding a common denominator, expanding brackets, the usual stuff. And finally, we use a really important trick that makes all this work. We assume our point P is very, very far away compared to the size of the dipole itself. And after all that math, boom, we get our first big result. The electric field on the axis is our old friend 1/4πε0 multiplied by 2 times the dipole moment P, all divided by r cubed. Now, two things here are super important. First, notice the field gets weaker as 1/r cubed. And second, look at the direction. The net field points in the exact same direction as the dipole moment vector. Okay, that was the axis. Now for part 2. What happens if we move our point to the dipole's equator? The line that slices right through the middle at a right angle.
So this setup is totally different. Our point P is still a distance r away from the center, but now it's sitting directly above it. This changes the geometry completely. The field from the positive charge now points up and to the side, and the field from the negative one points down and to the side. Since we've got these weird angles, we can't just add or subtract anymore. We have to break out the trigonometry and look at their vector components.
Here's where the magic happens. Because of the beautiful symmetry of this setup, the upward pointing part of the field from the positive charge is perfectly canceled out by the downward pointing part from the negative charge. They just vanish. So all we have to worry about are the horizontal components, which are both pointing in the same direction. We add those two together, do a little bit of geometry, use that same short dipole assumption, and we're home free. And here it is, our second key result. The formula for the equatorial field is 1/4πε0 times the dipole moment P divided by r cubed. Now hold on. Notice the two massive differences here. First, that 2 from the axial case is gone. And second, look at the direction of the field. It's pointing to the left, which is opposite to the direction of the dipole moment itself. This is a huge deal.
So we've done the hard work. We've derived both results. Now for the most important part, especially if you're studying for an exam, comparing them head to head. This is where real understanding happens. This little table sums it all up perfectly. Let's look at the formulas side by side. The only difference is that factor of 2 hanging out in the axial field. Now check out the directions. One is along the dipole moment, the other is opposite to it. They point in completely opposite ways. And that leads us to the final point on magnitude. For the same distance r, the field on the axis is always twice as strong as the field on the equator.
Let's just put that key fact on its own so it really sinks in. If there is one single relationship you burn into your memory from this entire explainer, it is this one. The axial field is double the equatorial field. This is a classic exam question, and now you know the answer.
All right, let's wrap this all up. We're going to distill everything down into a final cheat sheet. These are the absolute must-know points to make sure all this information is locked in.
So here are the takeaways. Number 1, the dipole field drops off as 1 over r cubed. That's way faster than the 1 over r squared for a single charge. 2, remember, these formulas only work when you're far away from a short dipole. And finally, the directions. Say it with me. Axial is with the dipole moment, equatorial is against it. Get those straight and you are good to go. And that brings us to the end. You've now mastered the 2 most important cases for the electric dipole field. But that leaves us with one last lingering question to think about. We know the field is strong on the axis and it's weaker on the equator, but is there a sweet spot somewhere else, at some other angle where the field just disappears, where it's exactly 0? Something to ponder for next time.